Now, on to gases, and our main man, Avogadro, is here again, and today we will be looking at his law, the final equation triangle, and some practice questions. And yeah, remember to download the free PDF so you can be making your own revision notes as we go along. So, on to Avogadro's law. So, somehow before balloons and the mole were even invented, Avogadro managed to fill a balloon with 1 mole of gas, and he probably started with oxygen, why not? He then did this lots of other times with some different gases, so he did it with methane, did it with some hydrogen, and he found that the volume of the balloons were the same. So it doesn't matter what the gas is, the volume of the balloon is the same. So we can see here, all of the balloons are the same size. He then very modestly called this Avogadro's law. Well, I'm not sure if this is all historically accurate, but Avogadro's law is a thing, and here it is. So it states that equal volumes of any gas at the same temperature and pressure contain an equal number of molecules. Impressive stuff. And yeah, and if you had 1 mole of any gas, its volume is going to be 22.7 decimeters cubed. So yeah, so all of these balloons here with their 1 mole of gas are going to be 22.7 decimeters cubed. So go back to the last video to remind yourself on how to convert between centimeters cubed and decimeters cubed if you have forgotten. And then so now on to our next thing. So molar gas volume. So this volume, 22.7 decimeters cubed, is called the molar gas volume. But this is only true at STP, and that stands for standard temperature and pressure. So the standard temperature is 298 Kelvin, so that's pretty much room temperature, and then the standard pressure is 101 kilopascals. And yeah, as we're going to find out in later videos, temperature, pressure, and volume are all linked. But back to today, we can now look at our final equation triangle, which links moles to volume. And how they're linked is via the molar gas volume, which is 22.7. So if you want to find out the volume, all you do is number of moles multiplied by 22.7. And if you want to find out your number of moles, it is just the volume, decimeters cubed, divided by 22.7. Nice and easy. Right, so let's put our newfound knowledge to the test when we look at some practice questions. Okay, so our first question is here. So what volume of carbon dioxide is produced when 360 centimeters cubed of propene reacts with 360 centimeters cubed of oxygen at STP? So that's the key thing. So the pressure, temperature is staying exactly the same. So for this, we don't need to worry about converting to moles and then back to a volume, because if we're working at STP, then the number of moles is going to stay the same. So what we're going to do first, so the first thing we're going to do is write out our balanced symbol equation, and then we can see that we've got 9 moles of oxygen reacting with 2 moles of the propene. So the oxygen is going to get used up first. So now we look at the number of moles of carbon dioxide produced, and we then are using this conversion factor here. So 360 times 9 divided by 6 is then going to give us our volume of carbon dioxide produced. There we go, nice and easy, nothing too tricky there, I hope. Okay, now on to our trickiest question for today. So what is the formula of an alkane that when 23 centimeters cubed is burnt in excess oxygen, we are getting 136 centimeters cubed of carbon dioxide? Okay, so there's quite a few things going on here. So first of all, we're going to write out a generic equation. So this is just a generic combustion equation. And then what we need to look at is some relationships. So in our alkane, we've got carbon and hydrogen, and all of the carbon from the alkane gets converted into carbon dioxide, and all of the hydrogen from that alkane gets converted into water. But yeah, the molar ratios are slightly different. So however many moles of carbon in the alkane, that's the same as the number of moles of carbon dioxide produced. Then for hydrogen, it is half compared to, so how many moles of hydrogen are in the alkane? Half the number of moles of water are produced, and that's because there's 2 moles of hydrogen in 1 mole of water. So you might not get a question exactly like this, but kind of knowing that relationship, this relationship that we've just gone through here, and knowing how the moles of carbon dioxide and the moles of water link to what's going on in your alkane or alkene will come up. This is a very popular sort of exam question that comes up all of the time. Okay, so now back to our specific question. So we know how much carbon dioxide we've got, so we can now calculate the moles of carbon dioxide. So so moles is volume divided by 22.7, converting the volume to decimeters cubed, and now we have our moles of carbon dioxide. So once we've got that done, we can now see how many moles of alkane we have. So the moles of alkane that we've got. So same as before, we're using exactly the same calculation as before, but just the number is a little bit different. So this time it's 23. So now we know the moles of alkane. We can now see the ratio between the two. So we have it in a 1:6 ratio. So from that, we can figure out that X is 6. So we know that X is 6. So going back to over here, so we know X is 6. So we know we've got 6 carbons in our alkane. And then using a bit of GCSE knowledge, we can then complete the formula for our alkane. As we know there's going to be 12 hydrogens. So there we go. So that is a few more steps involved there, but remembering this relationship is really, really important. Okay, on to our final example. So what is the volume of hydrogen produced when 6 grams of magnesium reacts with excess hydrochloric acid? So same as before, we have got our balanced symbol equation here. So why do we need this equation? Because we want to know the ratio between the magnesium and the hydrogen. And we can see that they are in a 1:1 ratio. So once we know the moles of magnesium, we will know the moles of hydrogen. And then once we know the moles of hydrogen, we can convert that to a volume. And that's exactly what we've done here. So moles of magnesium, so this is using an equation from a previous video. But the mass divided by the relative atomic mass, so that's going to give us 0.25 moles of magnesium. So this is exactly the same as the moles of hydrogen produced. So that's why we've got the 0.25 here, and then using the equation from today, so the moles is 0.25, and we're multiplying that by 22.7, and that is giving us our answer in decimeters cubed. But just for the fun of it, we can convert that to centimeters cubed by multiplying it by 1,000. Okay, happy days. All right, so that is everything from me today, and thank you as always for watching, and please remember to tell all of your chemistry class about these amazing videos and to like and subscribe for more IB chemistry content. All right, catch you in the next one.